All right, this is our section, finishing up our last section of chapter 11. And we're going to talk in 3D in this section. Some of what we're going to talk about is going to be very familiar, and some of it's going to be less familiar because you don't see it used as frequently, okay? So some of this stuff you're going to go like, oh, that sounds kind of like something I remember, but I didn't remember that exact word. So you're going to see a few of those kinds of things. All right, to talk about first, a plane is to 2 dimensions as a surface is to 3 dimensions. So this first one is surface. Okay, so if you imagine something in 3 dimensions that is a, tell me a 3-dimensional object you can think of.
Trash.
Okay, then the surface of the trash can is what we're talking about, okay? So it's not the trash can filled in as though it was a solid object. It's just the surface part of it. That's what we're referencing here. A simple closed surface has one interior, which is hollow or empty, and one exterior, and no holes. Okay, so you want to imagine like the box with the lid on it, not the box that's open. So there's definitely an inside of the box and there's definitely an outside of the box. What you don't want to imagine is a donut, right? It has a hole in the middle of it, right? Because that hole in the middle of it, is it outside or is it inside? The description's not clear, right? So if you imagine a hollow donut, it does not fit this description, but if you imagine a hollow apple fritter, that would work. Okay? There's the inside of the fritter, there's the outside of the fritter, there's no hole in the middle that causes sort of this weirdness, okay? A solid is the set of all points on the surface as well as the set of all interior points. So if you actually talk about the whole apple fritter now, we're good with that. Evidently, I have donuts on the brain, right? Okay. So the object that's actually filled in. So when you go to the store and you get, imagine getting a can of soda. The aluminum basically on the outside of it would be the surface. If it's completely filled and it's not, broken cap or whatever, the whole thing would be a solid, completely filled, right? You drink it out of there, and we pretend like we could lift the little tab back up. That would be the surface because it would be hollow on the inside. So that's sort of the difference of those. All right, so we're going to get some very clean, simple objects to talk about first. So this one is a very simple object, a sphere. A sphere is a set of all points that are a certain distance away from a single point. The definition is very similar to what? Do you remember hearing this definition before? Almost the same. What do you have, Emma? A circle. This definition is almost exactly the same as a circle. What do you suppose is different about this definition than when we had the circle definition without looking back at it? Any guesses? Yeah. Exactly. So when we had this definition for circle, we talked about it having to lie in 2 dimensions. So this is the 3-dimensional analog of a circle, right? It's every point that is a fixed distance away from the center. Right, we get a circle. So you're probably imagining something like, a ball, right? The distance from the center to the sphere itself is called the radius of the sphere, just like we had the radius of the circle. So all of that's sort of the same. All right, now we have polyhedron. This is the plural of polyhedra. So if I talk about one, it's a polyhedra. If I talk about more than one, it's a polyhedron. It's a simple closed surface with sides that are shaped like polygons. Okay, we've done polygons. We've done those the last couple of class periods. So polygons are shapes that have those straight edges, right? Rectangles, squares, quadrilaterals, pentagons, decagons, all of those are polyhedra. So if we take any of those objects and we create a shape with those objects only, not necessarily only one of those objects, you could have multiple of them, but only those types of objects, we create a polyhedra. So you see some shapes down here that some of them are and some of them are not polyhedra. So a few details about it before we look at which ones are and which ones aren't. We call the sides the faces of the polyhedra. So on the first picture, the face that's straight at us right here, this face is what shape? It's a rectangle, but the face on the bottom and the face on the top are different. They are triangles. So we can intermix the different shapes that we have, and still they're all called faces. The vertices, again, vertice is the plural of vertex, of the polygonal faces are called the vertices of the polyhedron. So it's all the corners. It's a fancy way of saying the corners. Okay, so vertices are the corners of the polyhedra. Faces are the flat objects, the two-dimensional objects. And then the sides of the polygonal faces are called the edges of the polyhedron. So the edges are these sort of line segments that match on the corners, that connect the corners. Let's say it that way. They connect the corners to each other. These are the edges of the polyhedron. So the first picture I've already talked about is it is a polyhedra. Okay, it's got triangles and rectangles. We're good to go. What do you think about the second shape? Is it a polyhedra? Yes, it is. I have what looks to be a square or a rectangle on the bottom, and then I have triangles on the sides. Can you guys get the three-dimensional picture of that one? That one's kind of hard to see. What about the third one? I mean, I know you know what shape it is. It's a sphere, but is it a polyhedra? No, it's not a polyhedra because it doesn't have these flat sides, right? It's actually aren't any sides, is what we would usually say. How about the fourth one?
No, because it's not a...
Again, we've got circles, right? There's a circle on the top, circle on the bottom. Those are not polyhedra. Those are not polygons. Polygons have flat edges, and circles don't. So it's not a polygon on the sides. It actually isn't around the object either. We'll have a name for that later today. How about the fifth one? Can you tell what this is?
It's a cube.
It's a cube with what?
Circle.
Yeah, like a hole cut out in the middle of it. Okay? Is it a polyhedra? No. And it fails to be a polyhedra because it's not closed, right? It has that hole in the middle like my donut example. But even if that hole in the middle weren't a hole, it's circular, it would still fail because of the hole issue. Okay? And then this one over here.
Yes.
Ooh, yeses and nos.
It's not simple.
It's not simple. Why isn't, what do you mean by, can you describe what you're thinking, Skylar?
It crosses over.
Yeah, it's not simple. It crosses over itself. It's almost like you have two polyhedra stuck together, kind of, right? If you could somehow detach it at that center point, then we would be okay. But because it's crossing over itself, it's not simple. Very good. All right. So here's our first category of shapes called prisms. A prism is a polyhedra with two congruent parallel faces called bases. And then the other faces are called lateral faces, and they're shaped like parallelograms. So here's my first picture over here. They're shaded in blue. Those are the bases. They're parallel, and they happen to be triangles. Okay? And then the lateral faces along the sides of them are actually rectangles on this one, right? Okay? Top and bottom parallel. This one is interesting because it actually has a right angle it's forming. So if you imagine like these triangles that are the base on top, the triangle that's base on the bottom, they're perfectly straight up and down from each other, vertically, right? Perfectly straight up and down, parallel. But not only are they perfectly straight up and down, they're like centered even the same. Right? That's what's creating that 90-degree angle at the bottom. So a prism is called a right prism if the lateral faces, oh, I didn't fill this in on my paper. If the lateral faces are perpendicular to the bases. Sorry, there is not enough space there to write this out. There's probably a shorter way to write that. But it is a right prism if we get that right angle. That's what it is. That right angle down there at the bottom tells us that. If we don't have that right angle, the prism is called an oblique prism. So the lateral faces are not perpendicular. Oh, that would be simplified. I'll use my perpendicular symbol. Then I have space to the bases. So oblique simply means that there's some sort of a slant going on. Okay? So the way that this is drawn, I know there's not a right angle drawn in here, but we look at this one and we presume, we believe that it probably is meant to be a right angle in there. Your book will be clearer than my picture. It has right angles when it means for them to be there. So this is probably a right prism. These other two are probably not. Okay? However, the bases themselves, I can't remember if this is my next slide or not. Yes, it is. We'll go to the next slide. The bases themselves are what create the name for our prism. Okay, so remember the bases are the parts that are top and bottom that are parallel. All right, those bases on the top and bottom parallel. The sides of a prism are always rectangular. Can you see that on every single shape here? They're all rectangles or parallelograms if it's an oblique one. This one's a parallelogram because it's tilted. But it's always a four-sided shape on the sides. So it wouldn't make sense to talk about the sides, the lateral faces, as being descriptive of the object. We're going to talk about it from the bases. So what we're going to do is we're going to take a look at what the base is that it creates. So tell me what the base is on that first picture. Are there 8? 1, 2, 3, 4. I think so too. Yeah. It's an octagon. So we call it an octagonal prism. And if it forms that right angle at the bottom, we would call it a right octagonal prism. Isn't that fun language? Yeah. Since we are not actually told that there is a right angle there, we'll just call it octagonal. Octagonal. I'm not even sure. I can't remember. I will tell you, I'm pretty sure it's not octagonal. I know that's what it looks like. I'm pretty sure that's not right. So octagonal prism. How about the second one over here to the right? I think there's 5 there. Over on the right-hand side of the screen. Are there 5?
Yes.
That's what it looks like to me. It's easier to count actually on the top, I think, than on the bottom of that one, the top base. And this one is clearly oblique, right? We know for sure that this one is. So this is actually going to have the word oblique in it because we can tell for sure. This one over here, the octagonal prism, it might be oblique or it might be right. We really just can't tell by the picture. If we were being the most descriptive possible, we should know which one it is and use that word. But this one over here, we know that this is octagonal or oblique. So this is a pentagonal. Oblique prism. How about the bottom left one? What's that one? Okay, and is it oblique or is it right? This one looks, again, very much drawn oblique. So this is a, I'm sorry, I should have written triangular first. I got carried away. Triangular oblique prism. What do you suppose that last one is over there? What's the base? It's a quadrilateral. It's probably a square or a rectangle, right? Nothing's marked, so it's hard to tell. Let's call it a square. Let's mark it so that we can give ourselves some indication of being able to write something down that makes sense. It should be marked, and it's just not on this diagram, so we're going to pretend that the diagram is marked for us. Then what shape would we have? It's a square.
You would have to have right angle.
Yeah, let me put a right angle in as well. Let's pretend like I had the right angle and it had the sides marked, all of that. Then yes, we would have a, just for fun, we'll just mark this one all the way up. Let's mark an angle right there too, so it's a right angle marking it down. So this would be a right. So this word right here should be the middle word, sorry. It's a square right prism. Square because the base is a square, right because the lateral sides are forming perpendiculars with the bases. Any questions on that? Those are prisms. Our next shape is pyramid. A pyramid is a polyhedron determined by a polygon base, a polygonal base, and a point at the top is called the apex. And the apex is not in the same plane as the face. that's on the bottom. Okay, so it truly has to be above, or technically could be below if you think about your prism being sort of inverted upside down or something like that. The pyramid's shape comes from the triangular faces. So all the faces, these lateral faces around the sides, they're all triangles. Remember, they were all parallelograms on the last shape, on the prisms. They're parallelograms. Now they're all triangles. The base can be anything, though. So this picture right here has a triangle shaded there on the base, right? It doesn't have to be a triangle. It could be a square or a rectangle or something like that as the base as well. It doesn't have to be a triangle. The pyramid's shape comes from, I already said that one, the altitude. That's the one I was on. The altitude is usually labeled as h of a pyramid, is a perpendicular segment from the apex to the base. Apex, not apeg, apex to the base. So let me draw in what you would normally see. You would normally see a line drawn in a right angle form, something like this. It's hitting that bluish shape on the bottom at a right angle, and this would be called the altitude, often marked with an A. Another word for altitude, in 2 dimensions, we often use the word height. Altitude is also synonymous for height. Yes?
Is it A or H? Because in the notes
Did they do H on there?
altitude.
Yep, they did. Your book's using H. My apologies. Thanks for letting me know. We'll mark it H. All right. Pyramids are named for their bases. So if the base is a triangle, it's a triangular pyramid. If the base is a square, it's a square pyramid. So when you think about the pyramids of Egypt, those are what? Do you remember? They're squares. They're square pyramids. Yeah, so those would be called square pyramids. If the base is a regular polygon, okay, so like if it's really a square or it's an equilateral triangle or it's an equiangular pentagon or whatever, then that will sorry, let me keep reading. And the altitude intersects the base's center. So the altitude, that apex line that goes straight down, actually hits in the very center of our object. Then it's called a right regular pyramid. Regular because we've got the base as a regular polygon, and it's right because it's, if you will, sort of straight up and down, right? Straight vertical. We get these perpendicular segments. And then if you have the altitude not intersecting the center, then it's an oblique pyramid. Okay. How many of you can draw well? I'm not going to make you draw. I'm just curious. Do any of you draw well? I do not draw well. So we're going to attempt to go through a little bit of how you draw some things in 3D. Okay? The drawing that I'm going to do an example of, I'm going to do an example of a prism one. Okay? So the idea of to draw in 3D, I'm going to write down kind of 3 basic steps. The first step is to draw the bases. And I say bases because I'm going to draw one that has 2 bases. If you were drawing a pyramid, you'd just draw 1 base. So draw the base, or bases. The second step is to draw parallel vertical segments of equal length. We'll say vertical congruent segments even. That's even better. And then the third thing is to connect the endpoints of the segments. All right, so I do have one advantage over you, is that I have the ability to draw straight lines. You guys can do it. I know you can. So we're going to draw something with straight lines. I don't even necessarily care what it is you draw. So if you don't want to draw the same picture I am, that's fine. What I'm going to attempt to draw is something with 4 sides. Or you know what? I'll just do 5 for fun. So here's my 5-sided shape. It is not regular because I can't draw very well. But you could draw it regular as well. So regular again means equal sides, equal angles. So this is step 1. You draw a base. Okay? Step 2 is not draw the second base if they're 2. Notice that? It's not. What do you do next? Well, what you do next is you actually draw these vertical lines. So what does that mean? Well, it means that you're going to take this line and go down like this. And then your goal is to draw another line segment of that exact same length. From every vertex, down or up or left or right. Your book is actually saying down, but you could draw it going up from where you are, or you could draw it going horizontal segments. And you have to do it for all of your vertices, however many vertices you have. So if you decided to be really creative and you drew yourself a decagon, you get to draw 10 of them. I drew a pentagon, so I have to draw 5. And even the one that's sort of hidden at the back, and if you want to draw it dotted, you can. But this is what you're actually going to be drawing. Our last step is actually to connect the end points of all of those lines, and it will connect, if we've done it right, in the same shape that we had above. That's how you draw a prism in 3D. If you're drawing a pyramid, it's even easier actually, because you actually don't draw vertical lines. You draw your apex and you just connect them. So if you had the shape of your image, and let's say you had this image, that's pretty close to what I drew before, and you had an apex, say here. What's that? I'm sorry. Well, you know what? That's the way it goes sometimes. Pyramids are easier to draw because you don't have to have those segments lined up. So this would be a pyramid. The apex and your single base, and then you can connect the endpoints. We're all just going to do our best. Okay? All right, some more vocabulary. Convex polyhedron. So just like convex shapes in 2 dimensions have the ability to stay completely and entirely inside of the shape, a convex polyhedron is a polyhedron where the segment connecting any 2 points is in the interior of the polyhedron itself. So if you take a look at the first one, that would be convex, but the second one wouldn't, right? It has this sort of indenture in the side of it that if I were to connect opposite points across that, I would cross outside my shape. The third one also would be convex. So the middle one, if it's not convex, do you remember what we called it? Concave. Yes, good job. All right. All right, here's some fun ones. I'm going to name them in a minute. If you're really anxious to see their names, you can flip to the next slide, but let's talk about what these are. These are regular polyhedron. They're convex polyhedron whose faces are all congruent regular polygons. So the first one, they're all equilateral triangles, right? The second one, I'm going to go down and back up. The second one down here is all equilateral, they're squares, right? If we go up to the middle one over here, what is this object? What are these sides and faces? They're triangles as well. They're connected differently than over here, right? It almost looks like there's a square or a rectangle in the middle. There's not. That's just the edges that you see that are forming sort of that shape. But it's the outside of the shape that you're talking about. This is triangles. Can you tell what this one is?
A pentagon.
They're pentagons, yeah. And then what about this one over here? More triangles, right? More triangles, very convoluted, sort of conceptually, it looks very complicated. All of these are called platonic solids. There are 5 of them. There are only 5 of them. There are no more than 5 of them. If you find another one, you might be famous. But you're not going to, I'm sorry. There really are only 5, okay? They have the same number of edges. What's it say? Each vertex at a regular polygon has the same number of edges. And then, like I said, there are 5 regular polyhedra. The 5 solid polyhedra are called platonic solids. Here are the descriptions of what these are actually called. So when it gets to your test, this might be something you want to jot some stuff down on if you don't remember all of these. This table is better than the one that's in your book because it actually shows you the number of faces and the number of faces at each vertex, which is a helpful piece of information. The thing it doesn't put on here for you, so you can reference your book, is your book actually talks about the angle measures as well at each of these. So if that's helpful for you, you can take a look at that one. The first one that has the 4 triangles that are equilateral is called a tetrahedron. The second one, you know that one. That one's cube. Okay, it's a cube. When we have the 8 equilateral triangles, that's called an octahedron. 8, octagon, right? But it's not octagon shapes. It's 8 triangles. Don't get confused on that. The next one we had was the pentagons. That is called a dodecahedron. Dodeca. Well, deca is 12, right? Do means, as a prefix, do you know? 2. So when we see dodeca, that's where you're getting the 12. So dodeca is coming from 12. And then the last one, 20, is icosahedron. We've got 20 triangles in that one. 20 triangles. Crazy stuff, right? 20 triangles. All right, what I want to show you next is something called a net. Not Annette, as in somebody's name. A net. All right, these are nets. What are nets? Well, nets are like taking the shape. Imagine that you had a ball that was made out of whatever you want to make it out of, but it has the sides, this ball, that are not surface, that are smooth, right? They're flat shapes. So you have the 4 flat triangles on the first shape, the tetrahedron. And if you cut along the edges in such a way that you were to be able to lay them flat, that would create a net. So this first shape right here that I was just referencing is right here in the middle. That is a tetrahedron cut and laid flat. Okay, so if you can imagine taking that shape and where you see the dotted parts, you fold it, it would fold up into the shape of the tetrahedron. Can everybody see that happening? It's a visualization thing, and I know that I'm not always good at visualization, but that's what's going on there. Cube was our actual next one on that image on that slide before. A cube, if we were to fold along the 2 dotted lines there, we would have to fold more than that. We would have to fold along here, 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 and here. It would fold up. So you can imagine the 4 pieces folding, and then this far one on the right-hand side is folding to be the top of the box. That's where that's folding onto. That's a cube. What was the next one on our shape? It was an octahedron. The octahedron is much more difficult to see. The more sides we get, the harder they are to see. But you can count it easier from this picture, right? Can you count the 8 triangles in that picture? You can. You've got your octahedron. Our dodecahedron down here in the right-hand corner, bottom right-hand corner, I'm sorry, left-hand corner, excuse me. Looks like pinwheels or something like this that are stuck together, right? Okay, again, this one gets more complicated, but as you can imagine this folding up, as you fold along this edge right here and it comes up, this piece and this piece connect, right? They form an edge of your dodecahedron. The same thing happens. This edge and this edge match up and they can sort of fill in the gaps. It's almost like looking at a picture of the globe, and they talk about the platonic shifts, right? How the Earth has shifted and how you can kind of see the images of where different fault lines have been before. And then the last one, the icosahedron, same thing. You've got lots of shapes in that one all folded up together to end up with that very interesting shape that we had over here in the bottom, very bottom shape right there.
those are the only shapes that will create nets, correct?
That's not true.
Oh.
These are the only regular platonic solids, and these are their nets. But nets happen for any shape that's a three-dimensional shape, okay? Yeah. Here, and that's actually where we were headed, so that's a good question to ask. Euler's formula. Euler's formula works for any polyhedron, not just regular polyhedra. So we just looked at the regular ones just a moment ago. So if you have any kind of polyhedron, the vertices, right, those are the corners, plus the faces, those are the flat sides, minus the edges, right, those line segments, always equals 2. It always equals 2. We're going to do one together, and then I want you to do 2 of them on your own to make sure that it worked. We're going to do this for at least 3 of our 5 regular polyhedrons. So which polyhedron would you like me to do? You get one of the 5 I'll do with you. Tetrahedron. Okay. Tetrahedron. You've got several slides that talk about the tetrahedron. What I'm verifying is that when I take the vertices plus the faces minus the edges, I get the number 2. So how many vertices are there in a tetrahedron? I think there's 4. We have one here, one here, one here, and one here. Are there 4? Okay. So we've got the number 4 down here. How many faces are there? Yeah, there are 4. In fact, this chart right here has the faces on it. So there are 4 on that one. How many edges are there? One, 2, 3, 4, 5, 6. There are 6. So if I take 4 plus 4, I get 8 minus 6 is, in fact, 2. All right, so we're going to pause right here, and I want you to take, you and a partner. Let's do this with a partner this time. So grab a partner, and you guys decide you're going to do the dodecahedron and the icosahedron, or whatever it was, whichever ones it is you want to do, okay? And you're going to choose 2 of them, and you're going to count vertices, you're going to count faces, you're going to count edges. And one of those, the faces, is actually in this chart, so you don't actually have to count those. All right? So give it a try. It is difficult to see. Let's take a look just for fun if we were to do the icosahedron. The icosahedron works out pretty nicely, I think, from the net. But you have to be careful because some of the sides are going to match up to the, like when you count edges. So the faces are easy. Wait, do we already have the face? Do we have faces already written down? Yes, so we had to define the vertices and the edges. Is that right? Okay. So when all of these fold up, you have to be careful right here on these edges that these 2 are the same edge, right? So you can't count that twice. That's one of the problems with nets, is you have to identify where the pieces are going to fold up. And so I don't know if I have any. I think I do. I'll see if I can find some actual polyhedron that I can bring in and you can touch and feel. I had one in my office at one point. I'll have to check and see where it went. My children play with things. They disappear occasionally, so we'll see. Let me mention it again, just so that I've said it twice. This works even if it's not one of these special shapes, these 5 special shapes. If you have any polyhedron, it's going to work. And remember, polyhedron don't have to be all the same shape. So you could have something that looks more like a soccer ball. Does anybody know what the little patches on the soccer ball are? Pretty sure it's hexagons and pentagons, if I'm remembering right. You get both shapes on there. And so it works. It's a polyhedron. It's actually not a ball. I mean, it's not a sphere. A soccer ball isn't. It's actually flat surfaces, to be honest. And so when you count them, you could actually count from that object, and it would still solve, and it would still satisfy Euler's formula. So, cylinders. A cylinder is a simple closed surface that is not a polyhedron. Wow, I always love definitions like that. It says they're not something else. A cylinder has bases that are not polygons, and one smooth lateral surface with no edges. The picture that you have in your mind right now, undoubtedly, is a right circular cylinder. You're thinking about something like a soda pop can of green beans, a toilet paper roll, or a paper towel roll. You're thinking about some of those objects. The circles are the bases, and it's flat, it's perpendicular to the surface that you're setting it on, right? That's called a right circular cylinder. If a cylinder is not right, it's called oblique. So it would be something that looks like slanted, something like the Leaning Tower of Pisa, right? It slants. Here's some images of cylinders. So this is that slanting one that I talked about right there. So this is called an oblique cylinder in the top left-hand corner. It is circular if that's really a circle on the bottom, right? So it could be an oblique circular cylinder. That wouldn't necessarily have to be a circle. It could be an oval, right? There's nothing in the description that says the bases have to be circles. So if you see this one over here on the right-hand side, that is definitely not a circle. But if, in fact, it is forming a right angle, which it might be, it could still be a right cylinder. It's just not a right circular cylinder. Okay? The last one here at the bottom, that one actually is supposed to show you that it is a right circular cylinder. You're creating that perpendicular along the lateral surface, which is this curved image, you know, like a sheet of paper towel, and you create that right angle with the base. So that would be a right circular cylinder. And those are indicating that there's, well, they don't actually write it down, but they're supposed to be giving you the image that it's really a circle on top and bottom of that one.
So with that, if you drop down the thing in the center, the apex, it would form a right angle?
Well, yes and no. There isn't an apex because an apex is a single point that connects to the edges, right? So we don't have what's called an apex. But if you had, you have these parallel images, right, on the top and bottom, these bases. If you took the center of each of those bases, they would form a perpendicular segment as well.
There's just
so
no name for it.
There's not a name for it,
Okay.
exactly. But the centers would be connected with a perpendicular line, a line perpendicular to the bases. Yeah. All right, our last object, cones. So a cone has something that's similar to that apex idea, actually. All right, so a cone is determined by a simple closed curve, which create a base, but the base is not a polygon. In the plane, simple closed curve in the plane, and there is a point that is not in the plane that is the vertex of the cone. So that point is serving as like our apex was for our pyramids. The cone has one smooth lateral surface with no edges. And undoubtedly, you're thinking of something like the yellow cones, which are not even quite exactly cones when you're out on the highway. Or you might be thinking of like an ice cream cone, which again, your best image would probably be a sugar cone, not a waffle cone. It's not going to work very well for the purpose of our discussion. If you imagine a sugar cone, it works pretty well. The line from the vertex, if it's perpendicular, the perpendicular line from the vertex down to the base is called the altitude. Just like it was called an altitude when we did it from the apex before. We can do the same thing we did before. If it's forming a, if the altitude comes down from the vertex at the very center of the bottom shape, it's right. You know, it's forming a right angle there, then we have a right cone. If it's a circle on bottom, right circular cone. If it is tilted or slanted, the altitude intersects somewhere else, it would be an oblique circular cone. It doesn't have to be a circular cone at all. The only pictures I have in here are circular cones, but you could have something on the bottom that was an oval shape, or that was a shape like this one up here with a point on top creating that cone shape. Right? That's that surface around the edges. Can you picture it? Okay. I think that's our last slide. Yeah, that's our last slide.